invoking from line 12. So that's exactly what we're going to say is we are on line 12, and when the subroutine returns, that's the only thing we have to do is to return that as my own return value. Are we doing okay so far with why the return info is just line 12, return, and then a question mark? Because the invocation itself is what is triggering the execution up to this point, and as a result, the invocation is replaced by a question mark. This is the last time we are invoking, because from here on, we're just going to return, 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 return. We go to the first line of action in the subroutine, line 7. This time it's easy, because B is greater than E is true. B has a value of 1, E has a value of 0. Okay. Now before I go any further, let's just kind of stop, take a step back, and find out exactly what are we doing. What is the question? What is this invocation of binary search trying to do? This invocation of binary search is trying to find out, this is my array. My array is column D to column F. Okay? It does not belong to me. I only have a reference to that array. The index of the first element, as far as I'm concerned, the index of the first element is 1. As far as I'm concerned, the index of the last element is 0. I'm trying to look for a value of 5. So the question is, can I find an element such that the element potentially starts with index 1, it potentially ends with index 0, and it has a value of 5? The answer is no way, because there's no such element to begin with, right? Okay, so that's why I can return false right away and say that, oh, you did not give me any valid range in the array to search anyway, so I'm going to return false and say, no element within this invalid range can possibly have the value of 5. And that's exactly what line 8 is doing, is saying, I'm sorry, but I don't know, I don't think so. There's no such thing. Returning false is just like returning 1, returning 0, and whatnot. You copy and paste the return info cell. This time you replace the question mark with the value of false. I don't want to spell the false, because it takes up too much space, so I just use an F to represent false. Is that okay? It's just a little twist of returning a numeric value. Instead of a numeric value, we're now returning a Boolean value, true and false. After line 8, we are done with the outer conditional statement, so we jump all the way to line 19. Line 19 now has a lot of columns to deallocate, okay? But it's still basically the same thing. Whatever columns we allocate for this invocation, we now free or deallocate all those columns. Are we doing okay so far? Where do we go next? The return info tells me where to go back to, right? So according to this, the return info, which is column S, is telling me that I should go back to line 12. Okay, so we go back to line 12. But when we are back to line 12, I should not be looking at column S to column X anymore, because these columns are deallocated by the time I execute line 12. By the time I get to line 12 looks like this, return false. Do we know how to return false? Is there anything else we need to do? No more invocations, right? It's all resolved. So now we go back to the context, which is column M to column R, and now we can execute return false. Now when we execute return anything, all we are doing is to copy the return info cell, paste it, and replace the question mark with whatever we are returning. Tell me again what we are returning. False. Very good. So now we are replacing this one with a false. After line 12, we are done with the inner conditional statement. Then we are done with the outer conditional statement. Then we are out to the end of the subroutine, which is going to deallocate all the columns that we have allocated for this invocation. And then we have to go back to wherever the return info is telling me to go back to. It's telling me to go back to line 14, right? Okay, so we go back to line 14, but the context is no longer M column M to column R because they are now deallocated. So that means, I know this is what I'm executing, but it's executing in the context of column G to column L. I'm returning false, but I'm using column G as my return info. So back to line 14 of the pseudocode, we are executing return false. Return false means I take whatever return info has, paste it here, replace the question mark with the value I'm returning, which is false, and I'm done with the return statement. Line 14 is here. After line 14, there's nothing else to do in the inner conditional statement, and there's nothing else to do in the outer conditional statement. So now we are going all the way to line 19 again, at the end of a subroutine. We deallocate all the columns that we have allocated for this invocation, and then we continue on to line 25, because that's what return info is telling me, is to go back to line 25 and continue with the execution like this. Now I'm back to line 25, but the context is now back to column C to column F. But what I'm doing on line 25 does not even need to know the context, because I'm just printing the value false to the screen. So I'm printing false to the screen or a piece of paper, and then we are done with line 15. Oops, line 25. Sorry. Is that what you're...
Yeah.
Okay. So on line 25, we print the value, and then we proceed to line 26. Line 26 is the end of the main subroutine, which means we have to deallocate all the columns that we allocated for the main subroutine. So the array itself is gone now. But this time, it is a return line number, which means it is quite simple. We just go back to post, and that marks the end of the entire trace. Are there any questions about this binary search algorithm?
I just had a general question. In the Visual Basic class, they were saying you should write programs that are easy to read and understand. The recursion programs seem to be much more difficult to follow and understand. So why do we use recursion programs instead of just doing loops and counters?
That's a good comment. Okay, I like that comment because you're bringing up a point that is very important. You can give me any logic, any pseudocode. If it has a loop, I can do it with a recursion. Okay. Now, on the other hand, you can give me any recursive subroutine, and I can turn it into a loop. Okay. So this is really important because what it is saying is recursion and loops are equivalent in terms of what kind of algorithm they can express. Are we getting the concept? So the question now is, when do we use recursion and when do we use loops? Because they are equivalent in terms of being able to express the logic of an algorithm. The answer to that question depends on the nature of the problem. Okay? Think about Fibonacci. Okay? Think about Fibonacci. So let's take a look at the definition of Fibonacci again. The definition of Fibonacci is, by definition, the Fibonacci number of 0 is 0. By definition, the Fibonacci number of 1 is 1. But the Fibonacci of n that is greater than 1 is defined to be the Fibonacci of n minus 1 plus the Fibonacci of n minus 2. If you look at this definition itself, it is recursive. So given that the definition of this is recursive to begin with, it makes sense to make a recursive subroutine to handle it. Right? Now, if you want me to, I can actually turn the subroutine of Fibonacci into a loop that does not have recursion. But the complexity of that loop is going to be way worse than the recursive version of this algorithm. Okay? So this is a natural problem, or the natural solution of this problem is a recursive subroutine. Okay? Now, in the case of binary search, you can argue either way. Okay? You really can argue either way because okay, this is an array that is given to me. Somebody told me already that I only have to look into this portion. The rest of the array cannot have the value k anyway. I only need to look into this portion here. Okay? That's the problem that is given to me. But I think personally, I think it makes sense to make it recursive because my job is just to see, oh, I'm just going to look at this element here, see if it is what I'm looking for. Because if it is not, I know that I would just tell whoever else, oh, look into this portion, see if k is over there. So this is actually, still natural to express this problem as a recursive problem because the smaller problem does resemble the bigger problem. Okay? Anytime you can break up a big problem into a smaller problem, but the nature of the smaller problem is the same as the bigger problem, recursion actually makes sense. Okay? There are other cases where recursion makes sense. Has anyone thought about, okay, let's say let me just give you an example. And this is something that, my micromouse students, had to deal with. I don't teach that class anymore. Okay, let's think about a maze. Well, 3x3 is not really that interesting, so let's make this a little bit bigger, 4x4. Okay, so here we have a maze, a 4x4 maze. And let's just say that, let's say a mouse or, okay. Okay, so my mouse is starting here. And it has to look for a particular item. And we don't know the mouse does not know where the item is. Okay, I'm just placing the item somewhere. So I'm putting the piece of cheese over here. Yep, having taught that class for so many years, I know how to draw a piece of cheese. Okay, so the question is, if you are going to write an algorithm to have the mouse to explore the maze to find the cheese, how would you do it?
You would need some kind of variable to store what you've already done that didn't work. So.
Okay, you do need that because otherwise you can end up in a loop and look into the same cell over and over again. But how do you systematically go through the maze and say, oh, I've been here already, let me go back. But when you go back to an earlier point, how do you say, oh, I have not explored in that direction from this cell, let me go in that direction? How do you express that? Recursion is actually the natural way of doing this. This is called a depth-first search. Okay, you basically go as deep as you can, but when you find a dead end, or if you go to a cell that you have already explored, then you backtrack. Okay, but every time you backtrack, you have to say, okay, this is the cell that I have been to already, but I have not turned around in that direction on this cell. Let me turn around and go in that direction and explore that direction as well. That's called the depth-first search algorithm. And in this case, that's exactly how some micromice would do it. Yep.
Are you storing the values of where you search? Search into a two-dimensional array to know?
In this case, yes, a two-dimensional array would be fine. But I can also show you the really, really abstract pseudocode. Basically the pseudocode would look like, define sub, search. Okay, in this case, it's a depth-first search, or DFS. And you will be passed, one parameter. Okay, you will be passed by value your current location. Okay. So what you do is you say, if the location is already explored, go back immediately. Okay, so you can say, if location explored, then return.